Hey y'all, today we're going to go over velocity time graph notes for physics. So velocity time graphs are graphs that are going to plot the velocity of the object as it moves versus the time. So you're always going to see velocity on the y-axis, and on the x-axis is going to be time, just like it was for position graphs. We're going to analyze these based on the shape of the lines, the slope of the line, and location of the line. So for the shape of the lines for velocity time graphs, we're only going to see diagonal lines and horizontal lines. We're not going to see any curved lines for velocity time graphs like we did for position. For the diagonal lines, if we see one of those, it means our object is accelerating. So for instance, for this graph here, our object would be accelerating from 0 to 2 seconds as well as from 10 to 12 seconds because that's where we have diagonal lines. Depending on which way the diagonal line is going will tell us whether it's speeding up or slowing down. For this example graph here, we start at 0 at 0 seconds, and at 2 seconds we're at a velocity of 8 meters per second. That would imply that we are speeding up. Our diagonal line here is going away from the x-axis. Versus over here from 10 to 12 seconds, our diagonal line starts up at 8 meters per second and then goes down to 4 meters per second. That implies that we're slowing down. We're going from a velocity of 8 down to a velocity of 4. So this diagonal line is going towards the x-axis. We're going closer to 0, therefore we're slowing down. This first one we were going away from 0, so we're speeding up. And then we'll see horizontal lines as well. This would imply constant velocity, meaning there's no acceleration. So from 2 to 10 seconds, for instance, this is a horizontal line. We're maintaining a velocity of 8 meters per second. Over here from 12 to 16, we're maintaining a velocity of 4 meters per second. If our horizontal line was on our x-axis, it would be sitting at a velocity of 0, would imply that the object is not moving at all. All right, so let's see how you understand this. So we have a graph here with a lot of different lines. This dark black line in the center, this is our x-axis, and then all these different colored lines are going to be different objects moving. So we're going to go through and see which lines represent different types of motion. So number one, traveling at constant velocity. So think about what kind of line you want to look for constant velocity, diagonal or horizontal. In this case, for constant, we want horizontal lines. So the only line here that represents constant would be this red line right here. It doesn't have any numbers to say what velocity it's going, but we know it's above the x-axis, so we know that it's not, as long as it's not sitting on that x-axis, we know that it's maintaining a constant velocity at whatever number that may be. All right, for number two, an object that is accelerating. What are we looking for here for acceleration? We are looking for diagonal lines. It doesn't matter if it's going up or down or if it's below the x-axis like the purple and green ones are. We just want diagonal lines. So in this case, for number two, our answers would be yellow, blue, green, and the purple line. All right, now for number three, objects that are slowing down. We know slowing down is a type of acceleration, and we want, for slowing down, we want a diagonal line that's approaching 0. So which lines are approaching 0? Yellow is pretty obvious. Most people get that one right. So it starts way up here, and it goes, as you read the graph, it gets really close to 0, so we know it's slowing down. The one that people get tripped up on a lot is this purple line here. They want to say it's speeding up, but in reality it's slowing down. It's just doing that in the negative direction, or it's doing it backwards. Think about putting your car in reverse and you're slowing down as you like back up out of your parking spot or something. So we're starting way down here at this high speed and we're getting really close to 0. We're just doing that as we're going in the negative direction, right? And then number four, an object that is speeding up. This one we want to go away from the x-axis. So the easy one to spot is the blue line here. We're starting really close to 0. And then if this was like a car, we step on the gas and we speed up as we drive away and get to a higher speed. The other one would be this green one here. We start really close to 0. It'd be like sticking your car in reverse and then pressing on the gas really and speeding up a lot. I don't really recommend doing that, but that would be kind of what is going on here. Right, moving on, now we can look at the slope of the line and how that represents the acceleration of the object. So when we find slope on these graphs, that's going to tell us the acceleration of the object. So if we have a positively sloping line, that means we're going to have a positive acceleration. If we have a negatively sloping line, negative acceleration. So for instance, from 0 to 2 seconds, this one is positively sloping, so positive acceleration, versus right here is negative acceleration because it's negatively sloping. If we have a slope of 0, like we would do from 2 to 10 and 12 to 16, we already talked about how that would be maintaining constant velocity. that also means then no acceleration. And then I put the slope formula on here again, just like from your position time graphs. Generally, most people stick with rise over run when they say what the formula for slope. All right, so now let's just calculate acceleration and do an example just to make sure you've got it. We're gonna just do for segments D and E on this graph. All right, so first up for section D on the graph is right here, and we wanna do rise over run. So the rise for spot D, it starts at 0 and drops down to -2. So your rise is -2. And then the units for that are going to be meters per second because that's what the units are on our y-axis are. And then the run, it goes from 55 over to 95. So 95 minus 55 is going to be 40. And then our units here is seconds because that's what's on the x-axis. So that's not really easy to do in your head. So you can pause for a moment and type that in your calculator. And that is going to equal 0.05 meters per second squared for that acceleration. So that's for D. And then for E, we want to go through and do the slope for that section. And that one starts at -2 and goes up to 0. So this time the rise is a +2 meters per second. And then the run goes from 95 to 105. So the run is 10 seconds. So then 2 divided by 10 is going to give us a slope of 0.2 meters per second squared. All right, so next up we can analyze the area between the line and the x-axis, and that's going to tell us the distance our object travels, or we can also use it to find displacement that the object travels during that time. So the area formulas we're going to use are easy ones that you learned back in like middle school or probably maybe even before that, but the area of a triangle and area of a rectangle. So for triangles, it's 1/2 times base times height. For rectangles, it's just length times width. So what you're going to do here, and we'll do any more examples later in the video too, is like, let's say I asked you for how far it went between 12 to 16 seconds. I would enclose this area between the line and the x-axis. In this case, once I connect that in, I get a rectangle, so I'd use the rectangle formula to do that. Or like in the beginning here, I get a triangle if I wanted 0 to 2 seconds. I would find the area of this triangle, or sometimes you'll get some funky shapes like here from 10 to 12 seconds. I don't get a perfect rectangle or triangle, but I can break this up and do a triangle and a rectangle and then add them together. So the last thing that we can kind of analyze with velocity graphs is looking at the location of the line and whether it's above or below the x-axis. If our line's above the x-axis, that's moving in the positive direction. And we kind of looked at that a few slides ago with those blue, yellow, green, purple lines. And the ones that were above the x-axis were moving in the positive direction. And if we were to do the area there, that would be a positive answer. And then if the line's below the x-axis, it's going to be moving in the negative direction. And if we solve for area, it's going to be a negative number. Okay. All right, so now let's do some examples, and you have this same graph on the bottom of your note sheet. So we're going to look through here first and look at this graph in terms of what it's doing. So we want to look for first, when is it moving in the negative direction? So in what time segments is it doing that? So when it's moving in the negative, we want to look for when it's below the x-axis. So it starts going below at 12 seconds, and then it stays below there all the way to the end at 21 seconds. So 12 to 21 seconds would be the answer for the first one. Then for the second part, moving in the positive direction. That's any time it is above the x-axis. So from 0, this whole time, it is above the x-axis. It may be speeding up, slowing down, or constant that whole time, but it's positive direction. So 0 to 12 seconds for that one. Then for the next one, when is it speeding up? When we are speeding up, we are looking for it going away from the x-axis. We're starting closer to 0 and getting further away from 0. So speeding up, we are doing that in the beginning, 0 to 3. Then we're doing that again, 6 to 9 seconds. Then we are doing that again in the negative direction, 12 to 15, because we're going away from 0 then, for right there. All right, and that's all the places that we're speeding up. And then let me switch colors again. All right, so now slowing down, we want to start away from 0 and go closer to 0. So right here, from 9 to 12, we're going closer to 0. And then at the end here, 18 to 21, we're starting away from 0 and going closer to 0. So both 9 to 12 seconds and 18 to 21 seconds. And then lastly, we want to know constant velocity. So with constant velocity, what are you looking for? Right, we're looking for horizontal lines, so from 3 to 6 seconds and from 15 to 18 seconds. That's when we have a constant velocity. All right, same graph. Now we're looking at the acceleration of the object in these time intervals. So when you're solving for acceleration on a velocity graph, what are you using? Are you using slope or are you using area? In this case, we want to use slope. So you're doing rise over run. All right, so from 0 to 3 seconds, we want to find that slope. All right, our rise here, we're starting at 0 and going up to 2, so our rise is positive 2. And then the run goes from 0 over to 3. And this would be meters per second over seconds. And you're going to type that in your calculator unless you're good at doing it in your head. You do not leave it in a fraction form. And you can round to 2 decimal places, and this would be 0.67 meters per second squared. Then we can go to the next one, 15 to 18 seconds is right here. You have a horizontal line, so without even doing the math, you should know immediately that that slope is 0 meters per second squared. But you can see my rise is 0 because I'm starting and ending at -2. So it'd be 0 over 3 seconds, which would be an answer of 0. All right, and then lastly, we have a 6 to 9 seconds is this diagonal right here. We're starting at 2 for our rise and ending at 5. So your rise here is 3 meters per second. And then the run, it starts at 6 and ends at 9. So your run is 3 seconds. So 3 divided by 3 is 1 meters per second squared. All right, now same graph, but we're looking at how far did the object travel during those same time intervals. So what do you think through what you want to use? Do you want to use slope or area to do this? The answer is you want to use area when you're finding how far it went. So from 0 to 3 seconds, we want to find the area between the line and the x-axis. So there's our line, the x-axis, and we want to close that off into a shape, and we get a nice little triangle out of that. So it'd be 1/2 times the width of our triangle, or the base of it. It starts from 0, goes to 3, so it's a width of 3 seconds. And then the height of the triangle goes from 0 to 2, so 2 meters per second tall. So 1/2 times 3 times 2 is just 3 meters because those seconds cancel out. So that would be for the first one. Then from 15 to 18 seconds, here's our line. We want to enclose it with the x-axis, so we're going to draw a line there and then connect it together, and I get a nice rectangle out of that. So here our width of our box is from 15 to 18, so that's a distance of 3 seconds. And then the height of the box, it is negative because it's below the x-axis and it has a height of -2, and that would be meters per second. And then multiply that together and you get -6 meters because your seconds cancel out. So that's for 15 to 18 seconds. And then lastly, from 6 to 9 seconds, I like to trace the line, and then let me switch colors here. Trace the line, trace kind of the x-axis, and then connect it together. So I don't get a triangle or a perfect box out of this. So what I want to do is break this into 2 parts and get a triangle and a box, and then I'm going to add them together. So for the box part of this, you have a width of 3 because it goes from 6 to 9. So 3 seconds, and then times the height of that box is 2 meters per second. And then I'm going to add the triangle, so 1/2 times its width is also 3 seconds. And its height starts at 2 and ends at 5, so it has a height of 3 meters per second. Right? You're not doing the height from the bottom, you're doing from the height where the triangle starts, which starts at 2, and this triangle ends at 5. So that's where I got that 3 from. And then you're just going to do all that math and add it all together. So 3 times 2 is 6 meters, and then 1/2 times 3 times 3 is 4.5 meters, and then added together is 10.5 meters. Okay? And that is it for this set of notes. Let me know if you guys need any help.